Hi guys, welcome back to Data Every Day. Today we're looking at a data set of weather in Szeged, Hungary from 2006 to 2016. And basically it has a bunch of weather data for a given day at a given time. I believe it goes hour by hour on various days from 2006 to 2016. And we're going to try to predict the visibility on a given day. So let's hop into the notebook. This will be more of a simple video, just focusing on data pre-processing. But we're going to use linear regression, decision tree regression, and k-nearest neighbors algorithm to make our predictions. So I'm going to import NumPy and pandas just to work with the data, and then the standard scalar and train test split function for pre-processing. So I'll go ahead and import those, and I'm going to load in the data using pandas.readcsv. And we can get the file path over here. Weatherhistory.csv. I'm going to paste that in, and we can take a look. Alright, we have 12 columns, and we can see we have 2 text columns. And I think for the purposes of this video, I'm not going to use them. Especially this one is going to have a lot of unique values. But if we were feeling very ambitious, we could definitely go through and use maybe the words as individual features in a bag of words format, or we could actually embed them as dense encoding. But for today's video, I'm just going to drop them. There are quite a few unique values even in the summary column, and so for the sake of simplicity, we will just discard those. I'm going to get some info on the dataset. You can see we have actually four object columns. The date we will be taking information from and extracting some features from there. The summary, like I said, we're not using. Precipitation type we will be using, and then the daily summary we're not going to use. Everything else is numeric already, and none of it is in categorical form. So there's not too much encoding we're going to do today. But let's get started pre-processing. So I like to make a function called pre-process inputs that's going to take in a data frame. It'll make a copy of the data frame. It'll perform all the pre-processing steps after that, and then it will return the same data frame at the end. This way I can get a sort of processed version of data. So here we have the original data, and then X will be our processed version. So I'm going to pass data into pre-processed inputs, and then you'll see we have this X. Currently they're identical, but now anything we do inside here, we can see the results on X. Alright, so let's start by dropping those columns I said I was going to drop. So drop summary and daily summary columns. So we're going to use df equals df.drop, passing in summary and daily summary. And we're dropping from axis 1, which is the column axis. Alright, then we can take a look at X, and you can see we now no longer have those text columns. And I guess next thing to do is work with the date. Actually, let's get a little more information. If we look back up here, you can see we have mostly no missing values, but there are a few missing values in the Precip type column, right? Because we have 96,453 total entries, and then in the precipitation type column we have less than that as non-null values. So there's some null values in there, and we can actually get the total number by using .isNA. This will give us trues and falses based on if there's a missing value in a given cell. And then we can sum across the row axis to get the number of missing values in each column. And you can see we have 517 missing values in the Precip type column. And if we're looking at what kind of data is in that column, we can actually get exact list of all the unique values using .unique. You can see we have rain, snow, or a missing value. And so when you're dealing with categorical data and you want to fill in missing values, it's best to use the mode, because I mean you don't really have another option. You can fill it with the most common occurrence, which is the mode, or you can just drop the rows. But I guess we will fill it with the most common occurrence. So if we get the mode of this column, .mode, you can see it is rain. Rain occurs the most. So currently this returns, look at the type of this. it's a series, yeah, pandas series. So to get the actual value for the mode, we're going to have to subscript it as 0. That will give us the string. So we want to fill in all the missing values with this rain, which is the mode subscripted at 0. So in here, let's fill missing values in Precip type column. And pandas has a nice function for that. It's called fillNA, which we just take the column. So Precip type equals df sub Precip type dot fillNA, and that will fill any missing values with whatever value we pass in. And the value we want to pass in is this one, right? The mode. Except we want to change data to df. Now if we run this, and we take a look, up here we have 517 missing values, but if we do the same thing on x, now this is our processed version of the data, you can see we no longer have any missing values in the dataset. Alright, so that has been taken care of. Any missing values have been replaced with rain. And now let's deal with this date time features. So datetime, pandas has a nice function called toDateTime that can take a value that looks like this, and it can convert it to a datetime object, which you can then reference individual aspects of the data. You can do .year to get the year, .month to get the month, .day, .hour, etc. And you can see in this particular data we have year, month, day information, and then we also have hour information. Everything else is left blank. And this here is the I believe the UTC offset, which probably not going to be so useful. We can just remove that. But this is in sort of an untraditional form for datetime objects. So if we use the pandas.toDateTime function, let's just use it on this column. So data sub formatted date. You can see it's actually taking a bit of time to process it. And that's because this is not like a standard way to encode datetime, because it has this extra information here. It actually has milliseconds here, and then it has the UTC offset. So you can speed up this process. Let's cancel that. You can speed it up by including a format here. And the format is basically a way of letting pandas know beforehand what kind of format the data takes, so it doesn't have to sort of figure it out on its own. So the way we can do that is we just do $sign and then the type of value we're looking at. So this means year. There's a full list of values on the pandas website. But we're gonna look at the year, and then there's going to be a hyphen, and then there's going to be a month, which is given by %m, lowercase m, and then another hyphen, and then get the day, which is %d, lowercase d, then a space, then the hour, which is given by %capital H, then a colon, then minutes, given by %capital M, then another colon, then seconds, given by %capital S. Then we have a period, and we have the milliseconds, and milliseconds are given by %lowercase f. And then finally we have a space and the UTC offset, which is given by %z. So now if we run this, it should take much less time to process. You can see there it is. And now what's good about this, how about we save it in DT for datetime? Well, yeah, okay, look at DT. Here we go. If we just take the first one, right, just this thing, you can see it's in timestamp form. What's good about this is we can type .year to get just the year, .month to get the month, and so on. And before we couldn't do this because this is actually just a string before we did this toDateTime thing. So what we're going to do in the pre-processing function now is actually get a bunch of different features out of this original date feature. So I'm going to grab that, and so we're going to extract date/time features from the, what is it called, formatted date column. Okay. And so here, this is going to first, we're going to convert it to datetime format. So let's actually take formatted date, and we're going to set it to a datetime version of itself, like this. So formatted date equals pd.toDatetime formatted date with the format we specified. And then after we convert it to a datetime, we're going to create year, month, day, and hour columns. Remember, all the other data is left blank, at least for these ones, and I don't see the purpose of putting that there. So we're just going to grab these 4 values. So we will have a year column, and all we have to do now is take the formatted date column and apply a lambda function to it that will look at each element x in formatted date and change x to whatever value we say, which here will be x.year. So it will take this date time and it will just take the year and store that in a new column called year. Then we can copy that over for month, day, and hour. This will be the month column. This will be given by x.month. This will be the day column, which will be given by x.day, and the hour column, which will be given by x.hour. Alright, and then once we've done that, we can drop the original formatted date column because it's no longer useful to us. We have all the information we need from it. So df.drop formatted date and axis 1 we're dropping from. And now if we take a look at this, this will just take a moment while it does the datetime. And you can see we now have year, month, and day columns, and I realized we didn't actually... the problem here is that this is just returning the data frame with the formatted date dropped, so we actually have to store it back in df. That's why the formatted date column is still here. But if we run it now, you can see we no longer have the formatted date column, and we have all the information we need from it in their own respective columns. Okay, and I guess the last thing to do here is to work with the Precip type column. We already filled the missing values, but now we want to change the values in there to be numerical values. So if we look at the Precip type column, and we can actually get the value counts, which will give us the unique values and how many times they show up in the column. You can see we have a bunch of rain and fewer snow examples, but these are our 2 values here. So we're going to, I guess we can encode snow as 1 and rain as 0. For binary columns like this one, where you have only 2 values, it's standard just to send one to 1 and the other to 0. So yeah, we'll pick snow as 1 since it's the sort of an anomalous occurrence. So let us binary encode the Precip type column. And to do this, it's very simple. Binary encoding is the simplest form of encoding. You just take the column, and actually we should be setting the column equal to the column, not the data frame. And we're going to apply a lambda function that takes an x. X will be a given one of these, which will be either rain or snow. And we'll send x to 1 if x equals snow. And otherwise, we'll send it to 0. And that's all you have to do. That'll automatically do the mapping snow to 1, rain to 0. This is also useful if you have a bunch of values and you want to just focus on one. You can send the one you want to 1 and all the others will go to 0. But in this case we only have 2 values. Okay, so if we run this, you can see we now have a numerically encoded Precip type column, and you'll see that the whole data set is now in numerical form. So I think we're ready to scale our data. Now one last thing to check is, let's see, like this one is sort of troubling me. I don't know much about this column, and when you're looking at the preview and you see that they all have the same value, it's a good idea to check out what kind of values are in some of these. So what I mean is we can get a dictionary that's going to map a column name to the length of unique values in that column. So we take x sub column dot unique and then take the length of the unique values, and that's going to be for every column in x.columns. And that will show us how many values are in each column. And just as I suspected, in the loud cover, I'm not sure if that's supposed to be cloud cover, but a loud cover column, we have only one value. And a column with only one value is not of any use, because it doesn't give you any additional information. It's essentially the same as putting a bunch of zeros in as input, because there's no difference between examples. So there's nothing that can tell the model something new. So let's actually drop loud cover up here. So summary, loud cover, and daily summary columns. So we're dropping that as well because it only has one unique value. And all the rest I believe are good. We know we have no other ones that have only one value. And yeah, it looks pretty good. This is all numeric, and I think we're ready to split and scale. So by split, I mean let's split df into x and y, where y is going to be the vector of values we're trying to predict. In this case, it's visibility. So we're going to take y to be df sub visibility. Actually, it's in kilometers like that. And then let's make a copy of it, and we'll store that in y. Then x will be everything else, everything except the visibility column. So here we'll drop visibility from df, visibility km, and we're dropping from axis 1, which is the column axis, and then let's also make a copy of that. Alright, now this will return two values, x and y, and if we take a look, we will now have our x and our y separately. Y is, oh sorry, x comma y equals, okay. Alright, so here's our x. We don't have the visibility column anymore, and the visibility column has been separated off into y. And so this is going to be the output that we compare the model's predictions to, and this is going to be the data we use to make predictions. And so it's a good idea to scale your data before you feed it into a model. There are certain models, like tree-based models, that do not need the data to be scaled, but many models will benefit from having scaled data. And by scaled data, I mean each column is going to take on a similar range of values. Right now you have every column takes on a different range of values. Precip type we know has either only a 0 or 1, whereas year goes all the way up to 2016. So we want them all to take the similar range of values, and for that we're going to scale x with a standard scalar. And a standard scalar, I'm getting that from sklearn. I imported it at the top here. Standard scalar is just going to it's going to give each column a mean of 0 and a variance of 1, so that most of the values in any column are going to lie between -1 and 1. So we can create a scalar object, so a standard scalar, and we have to fit the scalar to the data. Now here's the thing. We're going to split this data into a train and test set, and I'd like to actually do that first. I'd like to split into train and test set first, and the reason for that is I want to fit the scalar to only the train set, because in practice or in production you might not have access to the test set at the time of creating the model. So we only want to fit the scalar to the train set. I mean, we're actually only fitting the model to the train set also, so it makes sense. So let's train test split. So for the train test split, I'm using just the train test split function from sklearn, which is a great function that will not only split the dataset, but it will shuffle the examples for us first, which is very good as well. You don't want to feed an unshuffled dataset into a model. So that's going to generate 4 new sets of the data: x train, x test, y train, and y test. And that's going to be train test split. We're passing in x and y, and we're going to give it a train size of 70%. And we'll include a random state as well. The random state will ensure that the shuffle is always done in the same manner, and therefore the split as well. So 70% of the data is going into the train set, and the other 30% is going into the test set. And then with the scalar, we're going to fit the scalar with scalar.fit, and we're fitting only to x train. Then we're going to transform both xtrain and xtest using the fit that we have that's just on xtrain. Scalar.transform will do that for us. So we're going to transform xtrain, and we're also going to transform xtest. And you can see the fit has only been done to xtrain. So this will be our new xtrain, and this will be our new xtest. Scalar.transform actually returns a NumPy array, and I'd like to keep seeing the data like as a data frame, to get those nice column names there. So I'm going to turn it back into a data frame afterwards, and I'm going to keep the column names the same as they were before. So xtrain.columns. And I'll do the same thing here, except this will be xtest.columns. Even though they have the same columns, it doesn't really matter. Okay, so now instead of returning just x and y, I'm going to return xtrain, xtest, ytrain, and ytest. Okay, and let's load those values in here: xtrain, xtest, ytrain, and ytest. Okay, now let's look at xtrain once that's done. And you can see we now have scaled data. So each column has a very similar range of values. And if we look at the means of each column now, xtrain.mean, you can see all the means are very close to 0, right? Extremely close. And if we look at the variances, you can see they're all very close to 1. So the scalar has done that for us. If we do the same thing for data, we should have all different variances and all different means. Actually, I'm not sure if we can calculate mean. We might be able to, but there's some text columns in data. Whatever. They'll have different means and different variances, and after the scaling, they all have the same. Alright, our y has not been scaled. We don't want to scale our target. These are the values that we're actually trying to predict. And so now we have a nice input to our model and values to predict, so let us go into training. And actually, we could do ytrain here, because when we run the notebook, we won't have y anymore. Alright, and I'll just display the results as well. I'm not going to go crazy on optimizing these models. I'm just going to do 3 simple models and compare the results. So I'll make a dictionary that's going to map a model name to an actual instance of the model. And as I said, we're going to use linear regression, decision tree regression, and Neighbors Regression. So linear regression works by optimizing a linear function of the data. It optimizes a loss function based on predictions made by a linear function of the data. So we're going to have linear regression. That's going to be the name. So I'll make these double quotes. And we're going to map that to an actual instance of linear regression. Then we're going to have decision tree regression. And decision tree regression works with decision trees, which is basically just there's various algorithms to construct decision trees, such as the CART algorithm. Take a look at that if you want. But basically, it allows us to find non-linear relationships in the data that in a way that linear regression cannot. And for this, we're going to use the decision tree regressor from sklearn. And last, we're going to use k-nearest neighbors. So k-nearest neighbors, actually, it doesn't even use a loss function. It doesn't use any like stochastic gradient descent. This is actually just an algorithm that performs the regression for us. Probably the most simple form of machine learning. So this is the k-neighbors regressor from sklearn. Alright, I'm actually just going to indent these a little bit so that they all line up so you can see the scores next to each other. And now what I can do is take models.items, and that will return the key value pairs as tuples, and that way I can get the name and the model from each pair. So we'll fit each model to the train set, xtrain, ytrain, and then I'll just print out the name plus trained. So after each model is trained, it'll print out that that model has been trained. So we'll run that, linear regression trained, decision tree trained, k-nearest neighbors trained. So now all we have to do is output the scores, the r-squared scores in this case. By default, the model.score function from sklearn will give us an r-squared value, which is a measure of how dispersed the data is from our fit. So it's a measure of performance for a regression task. So for name model, again in models.items, we're going to print out the name, followed by a colon. Actually, we can put r squared and then a colon. I'll put a space there. And then I want to put the r squared value. I will display it to 5 decimal places. And we'll type .format, and I'm going to pass in model.score on, and I'm scoring on the test set, so x test, y test. All right, and it looks like linear regression did a terrible job. I mean, at least compared to the decision tree. Wow, it looks like k-nearest neighbors did the best with a 0.68 r-squared score. Decision tree came in second with a 0.5 r-squared score, and linear regression performed the worst with a 0.24 r-squared score. So sometimes the most simplest models can perform the best. It's very interesting. There's most likely no way to fit a linear line, to fit a line to the relationship between the independent variables and the dependent variable, and that's why the linear regression is performing so badly. But yeah, so that will conclude today's video. Thank you so much for watching. I hope you enjoyed. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.